All right, so today will be nothing new in T-charts. At this point and going forward from this point, especially after having turned in the giant packet of worksheets, I'm going to take for granted that you know how to do T-charts. If I tell you to go from mass of one thing to moles of another thing or whatever, I am taking for granted that you just know how to do that. Okay? However, what we're going to cover today conceptually might be difficult because this has less to do with how to do an actual T-chart and instead what that actually means. So we're going to go back to our old reliable So we've had this before. You're going to write this equation down for the 400th time in your notebook. And what I want you to pull from when you think of limiting reactants, I want you to pull from the s'mores lab that we did. How many s'mores were we able to make during that lab? 6. Why couldn't we make 7? We ran out of which one? Yeah, we ran out of Teddy Grahams. So in that reaction to make s'mores, in that reaction we ran out of Teddy Grahams. Teddy Grahams is what we would have considered our limiting reactant. We had excess, chocolate chips and marshmallows. You had some of those left over, correct? Yeah. So we're going to do the same thing today, only we're going to talk about actual chemical processes. And in this case, we're going to start with this one here. So in your worksheet, in your workbook, in your notebook, whatever, I'm going to say, what am I going to say? All right. Find the answer to this problem. In your notebook, ready, set, go. Now, some of you might be able to figure this out intuitively. Some of you may need to do a T-chart. Some of you may need to do 2 T-charts. But how much, in moles, how much water can we produce given 10 moles of H2 and 2 moles of O2? How much H2O can we make? My advice is to do a T-chart. Or 2. 3 might be excessive. Where's your answer? The Vietnam was a costly war. That doesn't seem very chemistry-ish. I mean, it's true. This is true. This is factual. But that doesn't answer the question on the board. I do. Anybody else? Last call on the worksheet packet?
There can only be 2 men.
Who has an answer? I know I've seen yours. What'd you come up with?
5 moles.
5 moles, okay. 5 seems pretty aggressive. 2, we got a 2, a 5, a 4. It's smart not to copy off Lubin this time.
It's 4. I never copy off Lubin.
That's good. It's good practice.
4.
All right, so you guys all have this written down, right? Yeah. So let's actually solve this out. I've rewritten our balanced chemical equation. Let's do some T-charts. So how much H2 did I start with? 10 moles H2, mole H2, mole H2O, mole ratio 2 to 2. How much oxygen did I give you? 2 moles? This ratio is 1 to 2. Why did I do 2 T-charts? Many of you only did 1. Some of you did none. Why 2? Yeah, so in most of the stoic problems you've had on worksheets, right? You had one thing, hey, here's your reaction. If you start with 10.3 grams of whatever, how many grams of something else did you produce or whatever? Right? But in this question, you were given 2 different things. You were given the amounts of both of the reactants. Right? I gave you in the s'mores lab, you get a bunch of chocolate chips, a bunch of marshmallows, a bunch of Teddy Grahams. We did the thing. You made as many as you could, and then you had to stop. In this reaction that we're doing here, right, it's hydrogen plus oxygen yields water. You're starting with some amount of both of these. You put them in a flask, in a vessel, in a whatever, and you start the reaction. And I did this T-chart 2 times and got 2 different amounts of water. Right? But which one did we actually produce?
4 moles.
The 4 moles. Why? Why didn't we make 10 moles of water?
Because that's what we already have.
Yeah, so we run out of something, right? Why couldn't we make 7 s'mores? Well, we couldn't make 7 s'mores because we only had enough Teddy Grahams to make 6. In this particular case, if we're given 10 moles of H2 and 2 moles of O2, we're only going to be able to make 4 moles of water because we run out. That is how we define this. This is the limiting reactant. Now, the important part here is to remember what we're talking about with limiting reactants. It's a reactant. So yes, we solved these 2 T-charts, but ultimately what we're after here is this part, the beginning of that T-chart. We kind of have to go back in time to where we started because we want to know which one of the reactants we run out of first. And that is limiting reactants. And so again, just like if you want to anchor this to something, I want you to think about the s'mores lab that we did and think about why we couldn't make more s'mores than we had stuff for. We ran out of one of the things. You gave me more Teddy Grahams. I could have made, I don't know, 1 or 2 more s'mores. I don't know how many chocolate chips you had left over or marshmallows or whatever. But this is the anchor point for all of this. So let's talk about this in steps. Here are the steps to figure out limiting reactant. Step one is pick a product. Now, in the example that we just did, that was really easy. Because there was only one product, we had to pick water. We're going to talk about in a second how you may make a better choice if you have more than one product. Step two is to do T-charts for both reactants to whichever product you picked. So in the case of being given, like we were in the last problem, some number of moles of hydrogen and some number of moles of oxygen, you just run two T-charts. And then once you've done both those T-charts to the same product, the lower number tells you that the beginning of that T-chart was then the limiting reactant. Like in our case, we figured out that that was the oxygen was what we ran out of first. Now again, this thing that we're doing today is more concept than it is how to do any given T-chart. At this point, you guys are all masters of T-charts. We're doing another fabulous worksheet packet because the last one went so well.
And 36% yield. I can't be living in these conditions anymore.
You'll make it, I promise. You'll live. Now, let's look at the first problem on here together.
It's gonna actually project out on that. In the packet.
So what do we have to do first?
Pray.
Pray. No. Not a bad plan, but no. Nope. Before we can even do that. Balance the equation, yes. Balance the equation is like a step 0. So get this balanced. We are doing it together, and by together I mean you guys are doing it separately. But we'll talk about it together in just a moment. All you got to do is balance it.
Yeah, you did. We have 8 on this side, so O.
As an aside, what kind of reaction is this?
2 is 6.
What kind of reaction is this? Nope.
Combustion.
Combustion, yes.
Thank you,
Combustion. All right, at this point, you all have balanced this effectively and correctly.
Yeah.
What is step 1? Pick a product. Now, what are our choices? H2O or CO2? Which one are you going to pick? And there's a right answer here. Why? Nope. I mean, yes. Let me be clear here. To get the right answer, it does not matter which product you pick. However, how I pick, I look at the rest of the question. Typically, when you have limiting reactant questions, there's going to be parts B and C and D and whatever. So I'm going to look at part B, and that's going to help me figure out which product I want to pick because I'm going to want to get that answer anyway. So given part B, what product should we pick?
I'm gonna pick O2.
What product should we pick given part B? Moles of CO2. Moles of CO2. So what is step 2? Now we've picked a product. We've picked what we want to solve for. What is step 2? T-charts for both of them. So you're going to have 2 T-charts here. Oops.
What are you supposed to do with the 4.8 and 2?
What?
So this is how I'm going to set up this problem. I picked my product. What I want to go to is moles of CO2, simply because that's what part B asks me. But again, we could go to some other product. We could go to the H2O if we wanted. I just picked CO2 because it smells like we're going to need that info for part B anyway. So why not do moles of CO2? What's left here is simply the T-chart. And again, I'm taking for granted at this point that all of you in this room can solve both of these T-charts. Maybe you need a periodic table, but you should all be able to do these 2 T-charts. This is the easy mode stuff. The hard part is setting this up and understanding it.
Wasn't joking, Haley. I was talking myself. Thank you.
O2 is a 5. 1. CO2 is a 3. 3.
That's not funny. Take me with. I'm still going. Not there. Still going.
Again, there's nothing on here that you guys don't know how to do. This is in this case, this would be a mass to moles problem, 2 of them. And now, given our result, what does this mean? What did we learn? Oxygen, 3.44 grams of O2 is our limiting reactant. So that answers part A of this first problem. We learned that because we did stoich on both of these initial reactants, and the smaller of these 2 products has informed us that our limiting reactant, our oxygen, is going to run out first when we do this particular reaction with these quantities. That is what we have learned. Now, since you did all the hard work here, what is the answer for part B?
101 won't.
Is it?
Yeah.
Is it?
Yes.
Could we make 7 s'mores in our lab? No, why not?
It's 1.
Yeah, we ran out of teddygrams. So in this case, we're going to run out of oxygen first. And as soon as we run out of oxygen, how much CO2 have we made? 0.065 moles of CO2. This is the answer to part B. And again, that's why I chose this in the first place. Because I knew I was going to need this in a second anyway, so why not pick a product? I picked moles of CO2. I'm going to need that in a second anyway. Save myself a T-chart. But again, we would have got the same answer even if we had gone to grams of CO2 or moles of water. We would have got the same answer. We would have figured out what the limiting reactant was, but then we would need another T-chart to solve part B. And I'm super lazy, so I want to do this all at once. And now here is the fourth step for these limiting reactant problems. And I didn't write this down. You may want to. For the rest of these problems in a limiting reactant problem, start with the limiting reactant. So look at part C. What does part C ask us? How much water can we produce in grams? Now, here's the beauty of this. What are we going to run out of first? Now, we already figured this out. We're going to run out of oxygen. So that becomes our starting point for subsequent problems. So in this case, to figure out grams of water, we want to start with our limiting reactant, 3.44 grams of O2. Have a T-chart, and at the end of it, we want to come up with grams of H2O. So again, this is just a T-chart. This is now a problem just like you did 100 of not last week, the week before last. Where now we simply need to go from, in this case, grams of a substance to grams of another substance using our balanced chemical equation. So that's easy enough, right? What was this? 5 and a 4. All right, so the rest of this is just math. So this is our answer for part C. Lastly, what is the question, or what does the question D ask you? Determine the number of grams of excess reactant left over. So let's start with, what is our excess reactant? C3H8. That is our excess reactant. But how much do we have left over? I don't know either, but I know it's going to start with a T-chart. So now I want you to think about this. When we will subtract, but we can't yet because we don't know what to subtract from. Okay, so stay with me here. This is where this gets difficult. In our lab, our s'mores lab, what were our excess reactants? Marshmallows and chocolate chips. How many chocolate chips did we have in excess? 4 or 5. I don't remember what the number was either. But it was some number of chocolate chips, was it not? So how did we figure that out? Yeah, you just counted them, right? You built your s'mores and you counted what was left. But ultimately, if you started with, I don't know how many were in there, 31 chocolate chips, and we used up 24 of them, how many did we have in excess? So we need to do a similar thing here. Okay, to find amount of excess remaining, we first need to start with our limiting reagent, because everything starts with our limiting reagent, reactant, whatever. Same thing. I'm making up new words. So the trick here is we need to find out how much of that C3H8 we burnt up in this particular reaction. So we need to go to grams of C3H8. We need to solve this T-chart first. We need to find out, we know we had extra, right? Because of that first problem we did. We know the limiting is the oxygen, so the excess in this case must be the other one. We have plenty of that left over. But how much? Well, to find out how much you have left over, you simply need what we started with, which the problem gives you, and we need to know how much we used. Well, to find out how much we used, we need to, again, start with our limiting reactant, and then just do a T-chart to figure that out. Now, assuming you've all gotten through your T-chart and done your math, you come out with this number. But what does this number represent?
The amount left over.
No.
The amount that
Yeah, this is not, we are not done yet.
yeah.
This only tells us how much we used. So we have to subtract it. So in this case, what do we start with? $13.85. This is part C, or D. You started with X amount. We used up some amount. And then to find whatever's left over, we simply have to subtract. we started with to what we ended with. And again, I want to reiterate, we haven't really learned anything new today. We haven't done any kind of crazy new T-chart thing. All we did was kind of put together what we know and how we can use something like a T-chart, whether it's moles or mass or grams or whatever. And now we can make a prediction when we react two things together, or three things, or whatever it is. We can now predict how much of something we would make based on running out of one thing or having too much of another or whatever. And this is limiting reactants.